Okay, so we are continuing on. It is week 4 out of week 12, so next week will be week 5, and the week after that is week 6, which is our midterm exam. So our midterm exam will be 2 weeks from today. So next week you have a quiz. It'll be the stuff I covered today. Next week I'm covering chapter 6. And so you do not have a quiz for chapter 6 by itself, but chapter 6 will be on the midterm exam. So I'll talk about the midterm some more next week as well. Yes?
I saw there's a study guide for the final. Is there a study guide for the midterm, or are the quizzes kind of like our study guide?
Yeah, so I would say use the practice quizzes 1 through 5 to study for the midterm. Okay, so I have a practice quiz for this week, so that's for this chapter, and then I have a practice quiz for chapter 6 as well, even though there's no actual quiz for chapter 6, but questions like that will be on the midterm exam. Okay.
Was not 1 through 6?
Huh? So
1 through 5 is midterm.
no, 1 through 6. Midterm will cover chapters 1 through 6. Okay. But remember, your first quiz covered chapters 1 and 2. So, well, anyway, I'll talk about it next week. It'll all make sense. I'm not trying to trick you guys or anything. Okay. I feel like I've been very fair, and it's my goal to be very fair. So, okay. Well, let's work here then. And this week we are covering chapter 5, which deals with probability. Okay? All right, so before I get into probability, I just want to do maybe just a very brief overview of the entire course. Okay, so to show how everything fits together. Okay, so in chapters 1 and 2, or actually 1 through 3, it was all about the basics of statistics, basic data description, okay? Basics of statistics. Statistics, okay? So we learned basic data description. Okay, and so how do we describe our data?
Numerical and categorical.
Okay, yeah, so data can be numeric or categorical. And how can we summarize our data? Okay, numeric summaries, right? So we have numeric data and categorical data. Okay, and we learned graphic displays. And we also learned numeric summaries. All right, so let's see if you do better this time, because I asked the same question last week and it didn't go so well. So what numeric summaries do we have for center? The mean, good. And the median, great, okay. What numeric summaries do we have for spread? Standard deviation? IQR, range, okay. All right, and I heard z-score, and that doesn't describe spread itself, but it does tell us how, what does a z-score tell us?
How much spread?
Not how much spread we have. It tells us about data points and how far the data point is from the mean. Okay, so z-score tells you how far a data point is from the mean. Okay, so this was all data description, and coming from data description, so let me just kind of write this. This is all. We had chapter 4, which was describing data when you have two variables, okay? Okay, so that was chapter 4. Okay, and this week we're going to work in chapter 5, which is about probability. Okay, so chapter 5 is about probability. And based on probability, we're going to go into chapter 6, which is next week. And that will be probability distributions. In particular, we have what we call the normal distribution. So we will see this next week. And the binomial distribution. So that's chapter 6. And then in chapter 7, we talk about sampling, okay? And this brings together the two sides, data description. So actually, I should bring that in there also. So data description and probability distributions come together when we deal with chapter 7, and we talk about sampling and inference. Okay. And I would argue that inference is kind of at the heart of statistics. Do you guys remember what I said is why the reason why we study statistics?
Make descriptions about a larger population.
Yeah, there we go. Okay, now I'm feeling good. So we've got the heart of statistics, which is statistics is all about making conclusions about the population that we can't observe directly from limited data. Okay, and that's what inference is all about. Okay, and so chapters 8 and 9, and I think 12, that's when we get into the nitty-gritty. Okay, and so the rest of the course is focused on chapters 8 and chapters 9, which is getting into the details of inference. And those chapters are probably, I don't know, tough. But I would say that's where the where lies the heart of statistics. Okay, all of this inference.
It's also the mid-chapter.
Huh?
It's a mid-section.
It's a mid
the book.
Of the book, chapters 8 and 9.
Chapter 7.
Oh, chapter 7. Okay, yeah, it goes right in the middle. And you know, if we had 16 weeks to get through the entire book, I would love that. But we only have 12, and so we're only going to get through chapter 9. Okay, so shucks. But that's what we've got. Okay, so anyway, if today's stuff feels like a departure from all of the other stuff that we've done, it's because it is. Okay, we're learning about probability. Okay, and we're going to learn about the rules of probability. And next week, we're going to learn about probability distributions, okay? And the truth is that the connection between this week and next week won't feel very strong, okay? And that's because there's a lot of complicated math that we're kind of just skipping over that connects Chapter 5 to Chapter 6, okay? And so there's, these very smart people did calculus to go from Chapter 5 to Chapter 6. We're not expecting you to have to do that derivations. I mean, you have to learn Chapter 5, the probability rules, and then we're going to learn basically if you apply that in kind of this complicated way, you end up getting these probability distributions. The distributions themselves are actually easy to understand, and I'm going to explain that next week. But if it feels like there's not much of a connection between this week and that next week, it's just because the math is complicated behind the connection. But that connection exists, okay? So nobody really questions why their cell phone works, but it does, right? And but there's a lot of science and a lot of technology behind this. But to use your cell phone, it's not so bad, okay? And so you can get great use out of your phone, even if you don't fully understand the technology behind it. We can get great use out of these probability distributions, even if we don't fully understand all the math behind it, okay? But we're going to try to cover some of the basics of probability this week. All right, is that good? So the midterm will cover chapters 1 through 6. Will be chapters 1 through 6, okay? And then the final exam will be everything we've learned, okay? So the final exam is everything. Everything but emphasis on chapters 7, 8, 9, and 12. Oops, I don't know what just happened here. Okay, there we go. All right, so here we go. We're going to enter the world of probability. Okay. So we talk about probability, and probability describes the likelihood or chance that an event will occur. We also have the idea of random, okay? Random, in a sense, means unpredictable, okay? Describes events where the outcome is unpredictable. Unpredictable does not mean that we cannot understand it, though, okay? We can, however, understand random events. Okay, so for example, we can flip a coin. Okay. And the outcome of the coin flip can either be heads or tails. Okay. And for any individual coin flip, we cannot predict the outcome. However, we can understand the nature of coin flips, or we do understand the nature of coin flips. Okay, and we can make a statement such as the probability that a coin flip will result in heads is 0.5. Okay, so we can say that. Okay, and is everybody comfortable with this statement here? Okay, nobody's shocked that I'm writing this. Okay, and so symbolically we can represent this same thing. Okay, I can write probability coin lands heads equals 0.5, or simply I can also just write probability of getting heads is 0.5. Okay. Now sometimes we leave off the R, and so these are also equivalent. If you leave out the R, you can just write okay. So this is just symbolically what we are writing here. The probability that a coin flip will result in heads is 0.5, and we're just kind of doing this shorthand. Okay, is that all right with everybody? Okay, and so when we talk about the probability that a coin flip will land heads is 0.5, this is what we call a theoretic probability. Okay, so these numbers are theoretic probabilities. Okay, theoretic probabilities are what we call, these are long-run relative frequencies, okay? Do you guys remember what a relative frequency is? Yeah.
I'm not sure. I just have a question.
Yeah.
What's the difference between P, PR, or
They're essentially the same thing. Just people might write P heads and people might write PR heads. Okay, this double arrow means they're interchangeable. Okay. You say tomato, I say tomato. It's that kind of idea here. Okay. So some books do this, some books do this. They're talking about the same thing. Yeah.
Would that infer that tails is 0.5?
Yeah, okay, so we'll talk about that in a moment here, okay? All right, so these are the long-run relative frequencies. Do you guys remember what a relative frequency is? It's the number that fits the category divided by the total count, right? And the idea here is if you flipped a coin, you know, 1 billion times, or, you know, millions and millions of times, you know, many, many, many times, and you kept track of how often you got heads and how often you got, and how many times you flipped the coin, that number that you get after millions and millions of coin flips should be 0.5. Okay. This is in contrast. So again, theoretic probabilities are the long-run relative frequencies. Okay, so basically based on an infinite number of trials. And on the other hand, we have empirical probabilities. Okay, which is the relative frequency based on actual observations or simulated observations. Okay, so for example, the theoretic probability for a coin flip so probability that we get heads is equal to 0.5. All right. So the empirical probability, on the other hand, would be based on actual observations. So let's say I flip a coin 10 times, okay? And I get heads, heads, tails, 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 heads, tails, heads, tails. Okay? So this is 10 flips. And how many heads do I have? I have 4 heads. Okay? So my empirical probability is my relative frequency based on actual observations. So my relative frequency would be 4 out of 10 or 0.4. Sorry, let me so my empirical probability of heads is 0.4. Okay. So this is based on actual coin flips. So pretend that these are actual coin flip results. And I've gotten 40% heads, and so there you have it. Okay, the theoretic probability, on the other hand, is 0.5. And we have something called the law of large numbers. Or the LLN. And this states that as you do more trials, your empirical probability will approach the theoretic probability. And so that's how casinos stay in business, because all of their games are set up in such a way that the casinos have a small edge in the games. So they should win a little bit. They'll win more, more than half the time. Well, any game with an even payout, okay? Whereas the player will win less than half of the time. And so, you might go to Vegas and you might quote unquote get lucky and win and walk away with some money. But in the long run, the more you play, the actual probability or relative frequency that you observe in your games will approach the theoretic probability, which are always in the casino's favor. Okay? Okay, and so the rest of today's lecture will focus on calculating theoretic probabilities. Okay? And empirical probabilities, again, they come from actual trials or simulations. But the rest of our lecture today will focus on the rules behind calculating theoretic probabilities. Okay. So far, so good? Or do I need to go back? Oops. That's my famous dog picture. Let's, okay. Facts about, okay, so let's just start off with some basics, okay? So we might have, we might define an event as A, okay? So there's some event called A. Okay, so A could represent, maybe A represents the coin lands heads. Or maybe A is, it rains tomorrow. Or A is, you know, Chris Paul makes his free throw. Whatever it is, okay? So it's just some event with a defined outcome, that's A, okay? And then we say the probability that A happens A occurs is probability of A or probability A, okay? You can write it either way. Okay? So do not, and we're going to assign numbers to these things, okay? So, and we assign numbers to the probabilities. So for example, you know, A is coin lands heads. Then we say probability of A is equal to 0.5. All right? But do not write A equals 0.5. Okay? Is the distinction here clear? Because A is the coin lands heads. It is not a number. It is not 0.5. However, the probability that the coin lands heads is 0.5. Is that, I hope that's clear to everybody, that we only assign numbers to the probability, not to the event itself. The event is the event. Okay. All right, so all probabilities So this is one rule. Okay, so all probabilities are between 0 and 1 inclusive. Okay? You cannot have a probability bigger than 1. You cannot have a probability less than 0. Okay, so if ever in your calculations you get a probability bigger than 1, you know you've made a mistake. You know that cannot be your answer. If ever in a multiple choice test you see one of the answers for a probability bigger than 1, you can eliminate that right off the bat because you know it's not possible. Alright, can I go to the next slide? Okay, we have what we call complements. Okay, complement of an event. So the complement, this is spelled with an E. It's not a nice thing you say to flatter someone that you like, but the complement of an event is the event when the original event does not occur. Okay, so complement, so the complement of A is basically when A does not occur. So if A is, the coin lands heads, okay, the complement of A would then be what? The coin does not land heads. Okay, so we might say, so if the coin can land heads or it won't land heads. Okay, so that includes the coin disappearing in the middle of the air, vanishes somehow, supernaturally, or an eagle swoops out of the sky and eats it, or it rolls away. The complement of A is everything that where it does not land heads. Yes?
And so there can be, not for this specific example, there's only two sides, but there can be more than one complement.
No, there can only be one complement, okay? Either this happens, either A happens, or it doesn't. There's no other possibility. Either A happens or it doesn't, okay? And so either it lands heads or something else happened. Now we can simplify the world and say, well, if it doesn't land heads, then it must mean it lands tails, okay? And we can say that. But, you know, if the coin lands on its side, then we would have to say that that doesn't count, okay? But, so it's either A happens or A doesn't happen, okay? And that's it. There's no other possibilities, and that covers all possibilities, right? Either this is true or it's not, okay? There's nothing else possible. So we say the complement of A can be written a few ways, okay? Complement of A can be written A with a C, okay? Or, okay, so I'll be right, can be written AC or not A, or sometimes A prime. This is like an accent, and it means prime. And basically, these are all equivalent. And so our book uses A complement. I kind of just like using not A, I think. That's what we say. And when we're talking about probabilities, then the probability of not A, or the complement of A, is equal to 1 minus the probability of A. Okay? So if A is the coin lands heads, and the probability of A is 0.5, then the complement, A not A, would be coin does not land heads. And the probability of not A is equal to 1 minus 0.5, which is also 0.5. Okay? So let's just make sure we understand. Let's say I've got a jar, and it's full of cookies. It's a good jar. Okay, and we have chocolate chip cookies and oatmeal cookies. All right. Okay, so let's say there's two types of cookies. All right, chocolate chip and oatmeal. Oatmeal raisin. Right, these are okay, and so let's say the probability of grabbing a chocolate chip is equal to 65%. Okay? So what is the probability of not getting chocolate chip? Okay? Will be 35. 1 minus 0.65. Okay, and then we can also, over here, we can say not chocolate chip means oatmeal raisin. Okay, so we can define the complement to be this. Okay, so that means what's the probability of getting oatmeal raisin? 0.35. Yes?
Why were you able to define what not chocolate chip meant there, but not in the coin toss? Like the coin could have gone anywhere.
Well, so
Like,
I mean, you
tails.
can define not landing heads means it lands tails. You can do that.
Yeah.
Yeah,
But
you
that's
can.
in-
Well, I just wanted to distinguish that not heads doesn't necessarily mean tails. You can define it that way, and you can say we're going to simplify the world, and we're going to eliminate any outcomes that aren't heads or tails. Okay. And I guess, you know, when you reach into the cookie jar and you, with the intention of pulling out a cookie, I guess there's other things that could happen, right? While you're reaching in the cookie jar, the world could explode and you never actually get a cookie, okay? Or, you know, maybe there was actually a monster in there and it bites off your hand. I don't know. Or, you know, your wife yells at you and says, "Don't eat a cookie." So maybe anything happens. But we can say, okay, we're going to just eliminate all of those possibilities and simplify it and say there's only two things. You either get chocolate chip, and if you don't get chocolate chip, then that means you got oatmeal raisin, okay? Whose favorite cookie is oatmeal raisin here? Oh, okay, we have a few. All right. Usually it's the like least loved cookie, and the but I don't know. Well, you know, in America we love Oreo cookies, but many international people are disgusted by the idea of some mysterious white cream in the middle of something, right? So, you know, I don't know how non-Americans feel about oat milk cookies. BuzzFeed's always making some video about some nationality tries some other nationality something for the first time, right? So, which I guess is entertaining. All right, we have what we call simple outcomes. Okay, so with simple outcomes, you might have a list of possible outcomes. So you have several possible simple outcomes. Okay, and each of these simple outcomes have the same probability. Okay, and so for example, a coin flip, we can say has two outcomes, heads or tails, and they are equally likely. Or rolling a die. You can get 1, 2, 3, 4, 5, 6. They're all equally likely. Or pick a card from a shuffled deck. Okay, then all cards have an equal chance of being selected. Okay, and so if you define another event as kind of either one of these simple outcomes or maybe a grouping of the outcomes, okay? So you have some other event. Some event which is either one or multiple simple outcomes. Okay, and then we say the probability would then be probability of A is equal to the number of outcomes in A divided by number of all possible outcomes. Okay. So I could ask, what is the probability I roll a number larger than 4? Okay, so our event is roll a number bigger than 4. Number larger than 4. Okay, so we'll just call this A. So the probability of A, so what are the outcomes that I can get that are bigger than 4 when I roll a die? 5, and 6, right? Those are the only outcomes that are bigger than 4. And how many outcomes do we have? We have 6 outcomes. 1, 2, 3, 4, 5, 6. So I'm using curly braces to indicate that those are the outcomes. So I have 2 outcomes that satisfy being larger than 4 out of a total possible of 6 outcomes. So the probability of A simplifies to 1/3. Okay? Or we can turn it into decimal form and say this is 0.33333, so on and so forth. Is that okay? All right. Just watch out. This only works. What is the rule about simple outcomes? Is that all simple outcomes have the same probability. Okay? So it does not work if we asked what's the probability that a family has 2 children. Okay? So what are the possible outcomes for the number of kids that a family can have? A family can have 0 kids, 1 kid, 2 kids, 3 kids, 4 kids, 5 kids, 6 kids.
20 kids.
Yeah, 20 kids, okay? So, you know, let's say the limit on family size, let's say, I don't know, I think the most number of children born to a single mother is like 60 kids, okay?
60 kids.
Yeah. Well, so she got pregnant quite often, but many of them were multiple births. Okay, so like she had some genetic predisposition to have like triplets, or twins and triplets, and she got pregnant many times and had many twins and triplets for a total of 60 children. Huh?
Are you serious?
I don't know. Go. Let's. During the break, we'll go on Wikipedia and we'll look up record for most number of offspring. Well, Genghis Khan had. Well, it's different for a guy, but anyway. Okay. So let's say. Let's just realistically, let's say anywhere from 0 to 20. Okay. So technically, there's 21 possible outcomes, right? 0 all the way up through 20. That's 21 possible outcomes. But each of those are not equally likely. You are not equally likely to find a family of 20 children as you are finding a family of 2 children. Okay? So you cannot do these calculations and say, oh, the probability that a family has 2 kids is 1 out of 21, because they are not equally likely. So it doesn't work that way. But if things like rolling a die, flipping a coin, picking a card from a shuffled deck, that works. Simple outcomes. All right. Another situation is, we can have maybe a table, okay? So here we asked a whole bunch of people, and we said, how much education did you complete? Okay, and so some people said less than high school. Some people will say high school. And some people will say college. Okay, so we've simplified it like this. Okay, and we ask, what is your current marital status? Okay, so we have single, never married. And we have married, currently married. We have divorced but not remarried, okay. and widow, widower, not remarried. And I think that covers all outcomes, and these are the numbers that we have. So there's a total of, did I leave something out? Okay, well I'm also just copying the table in the book here, okay? So these are totals. Okay, so we have 17, 68, 27. Okay, and so we can say I will pick one person at random from this group of 665 people. Okay, so in this case, each person is a simple outcome, right? Each individual can be considered a simple outcome. Okay. We, however, don't have the listing of raw data. We instead have this. And what do we call this table? Okay, what kind of summary table?
Frequency table.
A two-way table. A two-way table was what I was looking for, right? Because we have two, what kind of variables? Numeric or categorical? What kind of variables do we have? We have two categorical variables, right? Two categorical variables. So this thing is called a two-way table. What are our two categorical variables? Education and marital status. Okay, so we're going to ask some questions here, okay? Okay, so I pick a person. So all of these start off with the premise, I will pick one person at random, okay? So I pick one person at random. From the 665 people. Dot, dot, dot. Okay, so first question. And don't shout out the answer. I'm going to write these up. I'll give you a minute to figure these out. What is the probability this person completed high school? And B, what is the probability this person is divorced, not remarried? What is the probability this person is single single, never married, and completed college. Or, you know, I guess went to college, we'll say. Okay, so take a minute to answer these 3 questions. If you're watching on YouTube, I'm pause the video here and complete these questions, and then when we come back, or no, in a minute I'll go over the answers here. Okay, let's take a look here. Okay, what is the probability this person completed high school? So I didn't intend for this, but after I realized this, I realized this actually was a tiny bit tricky, okay? Because who completed high school? Okay, 397 people completed high school, and those who went to college also completed high school, right? Okay, so right, so with simple outcomes, you know, we don't have a listing of all individual people, but we ask how many people are included in this event. Completed high school, we have a total of 397 people who completed high school, plus the 143 people who went to college, okay? And we divide this by how many total possible outcomes are there when we pick 600 out of 665 people, right? So we do 397, let's see, 397 plus 143, I have a total of 540 people, divided by 665, and I get 0.812. I don't know, it keeps going. 8120300 whatever, okay? I like to keep about 4 decimal places, so I'm going to just stop at 0.8120. Okay? What is the probability that this person I've selected is divorced but not remarried? Okay? And that would be how many people? We have 84 people total who are divorced. 84 out of 665. So I do 84 divided by 665, and I get 0.1263. Okay. So far, so good? Okay, and lastly, what is the probability that this person is single and went to college? Okay, so we have 27 people, and that's it.
Well, what I think is it's sort of the same problem before, because I assume
Oh, the divorced people. Okay, so I guess, okay. So I should have done single, never married, and went to college, but, okay. So, all right, so let me define this. Okay, so we'll say probability of single, never married, and went to college, and college will be 27 divided by 665, and we get 0.0406. Okay, but if I define it as just probability of single currently and college, then we have to add the divorced people who would then be considered single, and the widows or widowers who would also be considered single, okay? And so we would have 27 plus 15 plus 3 would be 45 divided by 665. And I get 0.067669, so that would round off to 0.0677. All right. Are there any questions on how I got any of these numbers? Everything so far makes sense to everybody? Okay, why don't we take a 10-minute break then?